Alright guys, let's take a look at here. This is something that goes through all of math about, like in pre-calculus, you should have had, where does something happen and what happens. So where does something happen is x. What happens there is y. So the location, where are there discontinuities? There's one at x equal -3. What type of discontinuity is it? Jump. Cool. Where's the next discontinuity? Yeah, at x equal 3. There's a couple answers I would accept here. Depends on which side you're looking. It's like a giant jump, right? So I would accept jump, or I would accept infinite, yeah. It's like an infinite jump, so it's like both of them. And then where's the next one? At x equals 6, there's a discontinuity of what kind? Removal. Kick ass. Okay. So if I had just said where are the discontinuities, you would have said at x equal -3, x equals 3, x equals 6. Next. So where is x? Where to say where? The answer is x values. So here, the first three are my anchor points. So I know f of -3 is 2. F of 0 is 0. F of 2 is -1. Awesome. And then I know so now I can let's look at 2. The limit as x goes to 2, what does that mean? What does it inherently mean? From both sides. So the limit as x goes to 2 from both sides is 0. So what do I put where? If you put a closed circle here, you're desperately wrong, because then it's not even a function, right? What's it take to be a function? What do you have to pass to be a function? Vertical line test. I love it. Right? I like it. So what do I put? The output wants to be 0, but does it ever get there? Because it's a freaking limit statement, right? But I know it wants to be 0 at 2, so I put an open circle. And then I know approaching it, weehaw, weehaw, and I'll worry about the rest later. And what about, so then I got, what is that, 5 is negative infinity, so the limit as x goes to so x goes to 5 is negative infinity, so what's that mean? Right here I've got I love it. And here's the problem, if you do this and put nothing else over here, you're wrong. Because this inherently means from both sides. It's a great time to be wrong about this because I'm not grading these. And that's a little bit tricky, so it's good to see that in action. Yes?
Why did it go from point 0 instead of point -1?
Where am I at? Where are we at? Which one?
It continued from y equals 0 versus y equals -1. Why did you choose y equals 0 versus y equals -1?
When did I choose that? So the limit is x, are you talking about this point right here?
Yes.
So the limit as x goes to 2 is 0.
Yes, but when we're working with 5,
Yes.
you continued the graph starting from from y equals 0, not y.
Oh, I didn't continue from here.
Yeah.
Because then that statement would have been false. What's that mean? That has as you go to x from both sides. As you go to 2, from both sides, the limit's 0. Otherwise, I would have had to say the limit from above is -1, the limit from below is 0. Yeah, you can see that. That's why I put those little things coming right off the limit from both sides. Okay, so I have little, and then I can kind of go from there as I do the other restrictions. Are you guys with me? So immediately, if the limit at something, let's see, does it happen again? No, of course not. Yeah, at -3, let's jump to -3. So the limit as we go to -3 is 2, so I can just kind of do, from both sides it's got to be 2. Right? So I draw little stems coming off of it. So it's going to be continuous through there. I already know that. It's kind of neat because the circle was filled in earlier. Let's see, what did I skip over? This guy. The limit as x goes to 0 from the right is -1, so what am I going to have to do from here? The limit as I go from the right is -1. So I just got to go. So as I approach 0 from above, the way I say it, but from the right, so I better make sure that I go to -1 as an output. And as I approach it from the left, it's supposed to go to 1. So what am I going to put right on 1? Open circle, and I'm approaching it from this side. Woo-ha. And then I think that's everything, because we already did this guy. So you can do whatever you want to over here. Whee! Just make sure it doesn't come back on itself, or else it's not a function. So yours probably does not look like mine, right? But it's got the major, that's got to look just like that. That's got to look just like this. That's got to look just like this. That's got to look just like this. Those problem spots have to look exactly the same. You fill in the shit in the middle, totally up to how you feel, right? I like it. Now look at number 3. I know piecewise functions are always kind of like hated. They're not that evil, really. There's a couple things immediately you can tell. Where do I need to check to see if it's continuous?
Equal sign. The equal sign.
So, like, how do you mean? So is x continuous? Yes, everywhere it's continuous. Is square root of x minus 1 continuous on its domain? Yes, it's a root, so it's continuous. What's wrong with this one?
As in the asymptote?
Totally at
0?
0, and it's 0 in the thing I'm considering. So it's discontinuous at 0, right? So it's asking you, determine where it's continuous. So it's not continuous at 0. Yes, sir.
Could you just say that it's continuous on its domain?
1 over x is continuous on its domain, totally. G of x is discontinuous at 0 because it's defined with a 1 over x at 0.
Okay.
So g of x, where is it discontinuous? At 0. Where else? So looking at the functions, the only one of them has a problem, and it's actually in the region, so I got to say it's discontinuous at 0. Where else? There's one other place I got to check. What other kind of discontinuity can there be with a piecewise function?
Jump?
Yeah, a jump, because I'm at -1, I'm totally switching. But what's the value at -1 for this? If x is -1, what's x? Oh my god. And if x is -1, what's this? So they would fill each other in. Aw. Let them do what they want to. You guys, so I have to check these transition points. So look at the freaking functions, of course, because then you can just see real quick where's there a problem. And then you got to look at the transition points, because that's where they could maybe not match up. So look at 1. So far the only problem spot, I love it. The only problem spot is x equals 0, because this spot here worked perfectly. It met right up. What about at 1? This would be at 1. This would be at 0. Shit. So the problem spots are 0. Still can't say spot. And 1, because it doesn't transition. It misses. That's what gives people trouble. Piecewise is a whole different function takes over at a spot. So 0 and 1 discontinuous. So where's this continuous? Negative infinity up to 0. 0 to 1. 1 to infinity. We will see a ton of interval notation stuff. Should not be a big deal. You should be all about interval notation. I like it. And the justify your conclusions would just be the discussion we had. There's a function with a problem. There's a transition point with a problem. Now these are the ones I think you are going to have the most trouble with. The better you know the shape of these, the easier you're going to have a time with natural log especially. What is this going towards? The inside is going to 0. And what does natural log do as its input goes to 0?
Become become.
No. Natural log of 1 is 0. This is natural log of approaching 0. What does the natural log look like? Can you draw it in the air? That's not a complete natural log. It looks like a root. Draw a complete natural log. So it looks like this. This is a very important piece, right? What the shit is this? Yes, negative infinity at or approaching 0 goes to negative infinity. You guys with me? What power do you put on something to make it very small? A negative power. So a really big ass negative power is going to get closer and closer to 0, right? So you guys semi with me? Because logs are powers. So as the powers get smaller, more negative, the output gets smaller and smaller, approaches 0. That's why that asymptote is there. So that's the answer, negative infinity. That's what natural log does while it's inside goes closer to 0. What does it do? It goes to negative infinity. So all I have to do is know the shape to do this problem. There's no algebra you can do here. Why would you? Even if you could, because you know the answer based on the shape of natural log. What can you do here? Should you do first? Just plug a 3 in, right? It's always a great idea. Try to plug a 3 in, and then you get 0 with 0. You can try it out. So what does that mean I want to do? Considering what this looks like. Factor it. I love the number of people that make the top so difficult. What do you do with the top?
Factor out an x.
Take an x out, yeah. That's what you always try first in GCF. And then the bottom, what's the bottom mean? Come.
X minus 3, x minus 3.
Yeah, x minus 3, x minus 3. So one of those x minus 3's cancel. Now look, it didn't totally kill the problem, did it? Do you guys see what I mean? There's another frickin' x minus 3 down there. So the top is basically 3. Right? Or 3.000. It's basically 3. What's the bottom? Look at this. This is what's going to tell me the answer. If I approach 3 from above, from the right, x minus 3 is always... No. What's the bottom going to? What's the bottom going to? 0. So it's going to be some kind of infinity, because it's finite divided by 0. Some kind of infinity. So what am I doing right now? Which frickin' infinity is it? Right? So what's the top? Positive. Close to 3, it's freaking positive, because 3 is freaking positive. What's the bottom always?
Positive.
Positive, because I'm putting numbers in that are just above 3. Minus 3 is going to leave a positive amount. So what kind of infinity is the answer? Positive infinity, that's it. If I was going from the left, this would have been positive over negative, it would have been negative infinity. This is one of those that go like that. So the answer here would be positive infinity. You might even want to put a plus sign just to really make sure that I know what the hell you're talking about. What the shit do you do with this thing? Does somebody have a better way to write this? Say, I do, Jeff, just cover it with white up. No. What is cosecant? What is cosecant? What is it?
1 over sine.
Thank you. So I can make this x over sine x. Now I can look at this. What's the top? And again, what's the bottom going towards? What sine of pi? 0. I can't let it go to pi because it wants to be 0, and that would make this freak out, but it's approaching 0. More importantly, if I go to pi from the right, what does that mean? So what does sine look like?
It's at -1. The point.
No. What's sine of pi?
Starts at
0. So it's going to go like this. So if I go from above, it is going to 0, but their values are always negative. That's what's important here. I know this freaking thing's going to be infinity. Why? Finite divided by 0. Which infinity is the question? That's where you have to really analyze this thing. So if I go to pi from above, sine is always negative. So it's x. What is x close to pi? Positive. Pi is positive. So that's positive divided by negative. What kind of infinity will this be? Negative infinity. You guys see how to look at these problems? You should be able to identify its infinity Then you got to take a second to figure out which infinity is it. Yes?
Can you give us an example of if it was just plain old?
Plain old does not exist?
Does not exist.
If I said x goes to pi without a plus, right? Why would that change things? Because what's sine from the other side of pi? So they just wouldn't agree. Then it would be plain old does not exist. Yeah. I like it. So it's only plain old does not exist when they just don't agree. Otherwise it's infinity, negative infinity, yeah. Or it could be an open circle, right? Okay. Well, that would be for continuity. Let me see. Cool, I like it. That's, let's see. That gets us through 2.5. 2.6 is going to be related to horizontal asymptotes. So I gave us a little bit of a preview for that. 2.7 is where we finally get into some like actual calculus stuff. We haven't really done any calculus stuff yet. Believe it or not. This is all groundwork for calculus stuff. I think that's enough for today. I kind of like to let you guys out early instead of giving you a break. I don't know if you've noticed that. Okay, cool. So I'll see you guys. Don't forget, quiz first thing on Thursday. And real quick. Please, dear God, please come see me. If you're having a lot of trouble with Chapter 1, come see me. I'm in the office right before class, but it's only like half an hour. So you can always come. Like right now, I got an office hours immediately, right now. So Wednesday, Thursday, I'm in there 9:15 to 10:55. I have an 11 o'clock class. Don't just sit there and go, well, this is my life. Shit. Come get help from somebody. Me, somebody. Okay. That's enough.